Hello, as always, we'll start this lecture also with the formulas. So, intensity by single slit diffraction is this, by double slit diffraction is this, and by grating is this. So, there is only one difference that in double slit, cos square beta term is included, and in grating, this term is included. The maxima in case of grating is given by this e plus t sin theta equal to n lambda, where n is an integer, and minima in case of grating is equal to capital N e plus t sin theta n equal to m lambda. Here this n is capital N is the total number of slits in the grating which are illuminated. Here m is from 1 to 3 to capital N minus 1. So this m can also be written as small n times capital N minus 1. And the missing order of fringes are the same in double slit or grating, and that is given by small n is equal to e plus d divided by e multiplied by m. So this is an arrangement to get maximas by grating. So light is incident at the grating and various principal maximas are viewed with increasing diffraction angle. Here at theta equal to 0 we get 0 order. Suppose there are a number of wavelengths in the incident light, or the incident light is a white light, then all the wavelengths will merge to get 0 order. Then first order will be according to various lambdas, and the second order will also be according to their lambdas. The first order is given by e plus t sin theta equal to plus minus lambda, and second order is given by e plus t sin theta equal to twice lambda. As we know that if n is increasing as from going from first order to second order, this theta will also increase, and this theta is the function of lambda. If the lambda is greater, then the pattern will be realized for a higher value of theta. So we'll get all the spectrum in first order, in second order, and in higher order also. So this is another picture for the same. This is the central principal maxima, this is the first order principal maxima, and this is the second order principal maxima. So we see that the spectrum is converged in this region in the first order maxima. But as we go to second order maxima, the spectrum is expanded in the region. This is known as the dispersion of the light. So dispersion of the light can be defined as the broadening of different wavelengths as they pass through the grating. We can find the dispersion power of grating. So the dispersive power of grating is defined as the rate of variation of angle of diffraction with variation of wavelength, and it is given by d theta by d lambda. So d theta by d lambda can be found by the condition for principal maxima. So to find d theta by d lambda, we will differentiate that condition. So the differential gives e plus d cos theta d theta over d lambda equal to n, or d theta by d lambda equal to n by e plus d cos theta. So it is clear that the dispersive power of grating is directly proportional to n, and that is the order of principal maxima. So we have already seen in previous slide that as we are moving towards higher order maximas, the dispersion is more, and that is clear by this expression. This d theta by d lambda can be found by another way also. So here if we have another value of lambda which is slightly greater than the previous value, then this theta will also be greater than the previous value. So for Lambda, the condition is given by e plus d sine theta equal to n lambda, and for greater value of lambda, and that is lambda plus d lambda, this condition will be given by e plus d sine theta plus d theta equal to lambda plus d lambda. This d theta is very small value because this d lambda is very small value. For very small value of d theta, sin d theta can be written as d theta and cos d theta can be written as 1. So if we expand this expression, we will get e plus d sin theta plus cos theta d theta equal to n lambda plus d lambda. Using e plus d sin theta equal to n lambda, we can simplify this expression as e plus d cos theta d theta equal to n d lambda, or d theta by d lambda is equal to n upon e plus d cos theta. This is the expression for dispersive power of grating. Now, if we talk about the resolving power of optical instrument, then we'll have to talk about the limit of resolution first. So the minimum separation at which the two objects look as separate is called the limit of resolution of an optical instrument. And the resolution limit of our eyes is 1 arc minute, and the resolving power is reciprocal of limit of resolution. More is the limit of resolution of any instrument, less will be the resolving power of that instrument. The image of an object by an optical instrument is diffraction maxima of the object, due to diffraction that happens when light waves from the object enter the objective lens of the optical instrument. An optical instrument is said to be able to resolve two-point objects if the corresponding diffraction patterns are distinguishable from each other. The resolution can be divided into two classes. One is geometrical resolution. We use this resolution in forming image of an object. And second is spectral resolution. And this is used in forming the spectra of light. The spectral resolving power of grating is defined as the capacity to form separate diffraction maxima of two different wavelengths, which are very close to each other. To find the resolving power of any instrument, Rayleigh criteria is used. According to Rayleigh, an optical instrument can resolve two light sources when the central maxima in the diffraction pattern of one source falls over the first minima in the diffraction pattern of other, and vice versa. Similarly, in case of spectral lines of two different wavelengths, the lights will be resolved when the central maxima due to one wavelength falls over the first minima due to other, and vice versa. In this example, suppose these are two different wavelengths, lambda 1 and lambda 2. If the difference between lambda 1 and lambda 2 is fair enough, then the principal maxima by both will be separated fairly, and we can distinguish between the principal maximas by lambda 1 and lambda 2. The difference between lambda 1 and lambda 2 decreases, the principal maxima by both come close together, and this is the minimum limit in which both lambda 1 and lambda 2 will give different principal maximas. In this limit, the maxima of one wavelength falls over the first minima by the second wavelength. So in the final image, there is a dip observed, and this dip can distinguish between lambda 1 and lambda 2. If the difference between lambda 1 and lambda 2 further decreased, then the maxima by one wavelength will come closer to the maxima of the another wavelength, and in this case the resultant curve cannot distinguish between lambda 1 and lambda 2, and in this case it will be said that lambda 1 cannot be resolved by lambda 2 by the grating. So we can find the resolving power of grating. To find the resolving power of grating, we will use Rayleigh criteria. In this picture, at point P1, the maxima of lambda wavelength is formed, and at P2 the minima of this wavelength is formed. At point P2 the maxima of another wavelength lambda plus d lambda is also formed. So this is under the Rayleigh criteria. So at point P2 the minima of lambda wavelength is formed, and the condition for this can be written as capital N E plus D sine theta plus d theta equal to m lambda. Here theta is the diffraction angle at P1 and theta plus d theta is the diffraction angle at point P2 in the screen. This m can be written as small n times capital N plus 1. At point P2, the maxima of lambda plus d lambda is also forming. So the condition of maxima can be written as E plus d sine theta plus d theta equal to n lambda plus d lambda. So this is the wavelength and this is the diffraction angle. So we can compare this equation and this equation, and we can put E plus d sine theta plus d theta value in this equation. So we get this equation and we can solve this equation to have value of lambda by d lambda, and that will be small n times capital N. Small n can be written also as n E plus d sine theta by lambda. So this is the expression for resolving power of grating. So therefore, in our formulas, one formula for resolving power of grating is also increased.